Hello. Well, we're continuing to solve differential equations of various different types. In the last video that I uploaded just a very short time ago, earlier today, we solved um, simple harmonic motion equations of the form d squared x by d t squared equal to minus k squared x. So that form of simple harmonic motion equation gives rise to the solution x is equal to a cos k t plus b sine k t. And of course, I also showed you how to work out the constants by using initial conditions, but that was only one video and we might revisit that in due course. So we won't labour on simple harmonic motion equations at the moment, but what I actually wanted to do was to show you how to solve non-linear ordinary differential equations of the form that we have here in questions 1 and 2. Now, I think I have an earlier video that actually does explain how to solve equations like this. But I'm going to go over it again. If I haven't already been over it, I do apologise. But we will make a start on these two equations here. So, how do we solve equations of this form? Well, first of all, as I said, we know they're non-linear because any differential equation like dx by dt, and I'll see if I can actually write this more neatly. If we have an equation where you've got a derivative raised to a power like 2, or it might even be equal raised to the power of 4 or something like that, or if you have x d squared x by dt squared plus let me see, you might have a dx by dt squared over here, and so wherever you've got a dx by dt all squared, or wherever you've got a coefficient x in this case of the d squared x by dt squared term, then you've got a non-linear ordinary differential equation. So if we just delete those, we can see that the two equations in 1 and 2 are of course non-linear differential equations, because especially in each of these cases we've got a dy by dx squared term here, and here we've got in question 2 we've got dy by dx all cubed. So the question is, how do we solve equations like this, because they do look rather complicated. Hopefully you'll find it easier after I've explained how to solve these equations and which types of substitutions one should use to solve them, because that's the crux really of the matter. One needs to use a substitution in these particular cases because we're just dealing with a variable y and a variable x, and especially since we have not got a y term here in this particular case, we can just go straight ahead and use a substitution. Dy by dx equals p, right? Okay, so we can use that substitution in both of these cases. So if we consider question 1, we can write question 1 as, so here we are, let's just write this down. So we can rewrite this as d by dx squared. Sorry, we don't want a squared there. So we've got d by dx of dy by dx equals to, and we'll leave the dy by dx let's see, squared term as it was in the original question. So what you can see is that since dy by dx is equal to p, we can just go straight ahead and substitute p in for dy by dx. So we've got a p there equals to p all squared. Sorry, my brackets aren't really brilliant, are they? So we've got a p squared there. Now we can just simplify that notation wise by writing it as dp by dx equal to 2p squared. Now, if you've done A-level mathematics or high school mathematics, you'll be more familiar with this type of equation here. We call this equation star. Right, because when you solve this equation, you write this as dp over p squared, and you put the integral signs in, and that's equal to 2 times the integral of dx. Now we're not putting limits in at this stage, but we probably will have a constant of integration. So you should know that the integral of, for example, as an aside, the integral of 1 over x squared dx is equal to the integral of x to the minus 2 dx, and that integrates to give x to minus 1 over minus 1, or if you like, minus 1 over x. So here we've got minus 1 over p equal to 2 times x plus a constant which we'll call a, and let's just bracket that off. Right, okay, so I'm actually going to do a little bit of manipulation here. I'm actually going to rewrite this, if we can just scroll down a little bit. I'm actually going to write this as 1 over p. And by the way, I'm just going to go back to that and call that a1. So we've got 1 over p is equal to, well, we'll call, we've got a minus a1 there, minus 2x. Whoops. Okay. So I've just rearranged this right-hand side slightly to get that. Now, I'm going to call that minus or negative a1 constant, just a. So you've got 1 over p equals a minus 2x. And you should be able to see that, if I could just scroll down a little bit more, let me just move that a bit up there. There we are. Right, so if we take the inverse of both sides, or in other words, if we cross multiply by p and divide both sides by a minus 2x, we get p, that is supposed to be a p, equals 1 over a minus 2x. Right. So what do we do now? Well, we know that p, however, p we know is dy by dx, if I've remembered correctly, and that is correct. So we've got dy by dx equal to 1 over a minus 2x. Now this is yet another differential equation, which is hopefully relatively straightforward to solve. And of course we write this as the integral of dy equals the integral of dx over a minus 2x. Right? So now if we integrate this, we've got y equals, well, how do we integrate the right hand side? Well, this right hand side, I'll just write a little section over here. You know that 1 over u du, or rather the integral of 1 over u du, is equal to the logarithm of u, right? So this integral is going to be, let me just get rid of those equal signs, I've accidentally put them in. So this is going to be equal to log of a minus 2x, but not quite, because something has to go in front of the logarithm. There has to be a coefficient in front of the logarithm. And what's that? Well, it turns out that you've got to differentiate the a minus 2x part, and of course if you differentiate a minus 2x, I'm going to erase this in a moment, but if you differentiate the a minus 2x, let me just make that look more like a d, then you get minus 2, okay? So we've got 1 over, and it's actually minus 1 over 2. So we basically differentiated the denominator to get the 2 there. And we're nearly home and dry. In actual fact, there should be another constant. So let's just erase this because it's just clogging up. Just clogging up the screen. So going from where are we? Going from here, right, so going from here to here, there should be another constant b, and if you had your initial conditions, you would be able to find whatever constants a and b actually are, but that is the solution to our first ordinary differential equation here. Now then, for the second equation, let's go down and write that down again. So we've got part 2, we've got d squared y by dx squared. Let me find where I am. Plus y dy by dx all cubed. Let me just scroll up a little bit there. So let me see, let's put the cube term where it looks more like a cube term. There we are. Oh dear, that's not very good, is it? I do apologise. Right, there we are. And that's equal to 0. Okay, we can scroll up a little bit more now. So using our substitution, dy by dx equals p, then we have let's scroll up a little bit. Then we have again dp by dx. Whoops. Plus y p. Oops, I keep hitting a button. But there's a problem here, because I told you that we use dy by dx equal to p, but the problem is we have a y here. We can't have 3 different variables, p, x and y, in the same ordinary differential equation. That's actually when it will become a partial differential equation, actually. So we have to do something more to this equation to get it into form where there are only 2 variables, say p and y. So if we look at this dy by dx up here, we have p. So we've got dy by dx equals p. This means that d squared y by dx squared is equal to dp by dx. But we've already got that there, and we don't want this. So this is the bit that we want to rewrite as something else. Now, using this expression on the right hand side, if I just move up a little bit, let me just scroll up a little bit, there we are. Right, so we've got dy by dx squared equals dp. And I'm going to write it like this. I'm going to shift the dx over there, and I'm going to bring another variable in here and here, both of which will cancel, therefore giving back the dp by dx, but we don't actually want to do that. So I shall just remove those, and since you will know, or you may have observed, we've got a y in here, which has complicated it, meaning that we have to transform this dp by dx here. So therefore we bring a y in. So we'll bring a dy there and a dy there. But we know dy by dx equals p. Let me make that look like a more convincing d. So what we actually have is dy by dx equal to, well, this bit is p, so we can write down p here, and the dp by dy stays as it is. So now, and by the way, I'm forgetting to put my squared terms in. That should be a squared term, that should be a squared term, that should be a squared term. Right, so d squared y by dx squared is equal to p dot dp by dy. So let's go back to our, we'll go back to our original equation so that we can see what we're doing. We've got a d squared y by dx squared term there, plus y dy by dx all cubed. So we can write, by substitution, p, right, so we've got p dp by dy plus yp cubed equals 0. Now, again, this might look a bit more complicated, but hopefully not so complicated that you haven't met this type of equation before. What I'm going to do first is take a p. I'm going to factorise a p out of this equation. So if I can avoid accidentally hitting this button on my pen, I should be able to write a p there, and then, well, I'm going to put square brackets in. It's a bit easier than to write curved brackets, you know. So we've got dp by dy plus yp squared equal to 0. Now, there are two cases to consider here. Either either p equals 0 or dp by dy plus yp, pressing the wrong button again, p squared equals 0. Now, if p is 0, we know that p equals 0 is p equals dy by dx. That's for this bit here. That's for that bit. Right. So therefore, dy by dx is equal to 0. So dy by dx, this p here is dy by dx is equal to 0. So that's what we've got here. And if you integrate that straight off, you get y equals a constant. And this is a special case of the general solution, right? And I cannot draw brackets to save my life, so there we are. It's a special case of the general solution. Now, let's just go back here. So we're left now with dp by dy plus yp squared. And I'm going to rewrite that again. I might have to refer back to it. So we've got dp by dy plus yp squared equals 0. I hope. dp by dy plus yp squared equals 0. Right. So, once again, as with the first question that we dealt with, we've got dp by dy equal to minus yp squared. This is generally the way that I do it. You could actually probably, thinking about it, I think you could use an integrating factor here, but we'll do it this way in any case. So we've got dp over p squared, and in fact I'm going to put the minus sign on that side, so that we're left with the integral of y dy, and you'll see why I put the minus sign on the left hand side, because as I told you, as I reminded you last time, 1 over x when integrated with respect to x, 1 over x squared, the integral of 1 over x squared is equal to minus 1 over x. Okay, but if you've already got a minus sign there, then that becomes plus. So what we've got here is 1 over p is equal to y squared, and I'm going to call this constant a again, because this is a separate question, right? And if we invert that, we've got p equals 1 over y squared plus a. But we know that p equals dy by dx. I hope. Let's just double check we have got that above. So p equals dy by dx, right. Therefore, we've got dy by dx, I'll put a therefore there, is equal to 1 over y squared plus a. Okay, now this, all you need to do with this is separate the variables. So if we multiply both sides by y squared plus a, and also multiply both sides by dx, we get this. And of course we're not putting limits in. Whoops. I keep pressing the button by accident. There we are. So now we can just integrate this straight away, and you get y cubed over 3 plus a y equals x plus another constant of integration, b. And what I'm going to do is what we'll do is we'll call that B B1. So we can rewrite this as y cubed over 3 plus a y minus b1 equal to x. And of course, since we're not actually working out the constants, we can once again let b or minus b1 equal b. So we've got finally x equals y cubed over 3 plus a y plus b, and that is our general solution for the second question, or the second ordinary differential equation. So let's just very quickly recap, if I can draw straight lines. So we wanted to solve the first equation, for which we obtained this logarithmic solution, and in the second question we have this non-linear ordinary differential equation, for which we obtained this solution, which is cubic. And so I hope that's been of use to you, and that it's helped you in your endeavours to understand some non-linear ordinary differential equations, if indeed that's what you wanted to know. And until the next video, which I imagine will be being posted relatively shortly, I bid you farewell and see you later. Okay, bye.